Hi everybody, welcome to another video in Linear Algebra, section 1.8, Introduction to Linear Transformation. A transformation or function or mapping T from Rn to Rm is a rule that assigns each x in Rn a vector T of x in Rm. The set Rn is called the domain of T, and Rm is called the codomain of T. Right. So let's see, we have Rn. That is Rn, and we have a point in Rn, and the map is assign x to T of x in Rm. Rm is another space than might be a different space than Rn. It is called the codomain. It's not called the range because the range is what we defined later. The notation T from Rn to Rm indicate that the domain of T is in Rn and codomain is Rm. X is in Rn. The vector Tx in Rm is called the image of x. So if we just have one point, like we have a point x in Rn, then Tx in Rn, and this is called the image of x under the action of T. The set of all images Tx is called the range of T. Right. Later on we will have say if we have a point here y, and that is a point that's mapped to y from Rn. Let's see, this is another point, maybe let's say different x, say x1, then we map x1 into y, and if we call y is an image, then we can call x1 is the pre-image. This is pre-image, that is an image. Yeah, we can also call like that. It is easy to assign some definition there, so like I said, we'll revisit that later. A matrix transformation. For x in Rn, Tx is computed as A times the vector x, where A is the n by n matrix, and we denote x map to h of x. So here we say Rn goes into Rn. That in general a space into a space. However, when we say x with this symbol, we mean x maps to h of x. So that's simple. An arrow with an special end point here. This is called maps. So we say x maps to h of x. The domain of T is in Rn, and the codomain is Rm, and A has n column, and m and each one has m entries. The range of T is the set of all linear combination of columns of A. Right, so let's say we have a map this is an x. X will be, let me this in the this is a vector x. Vector x, this way. Vector x will be in Rn. Therefore, we can say this one has n rows and one column. It is a vector x. So this is x. Will be equal to we have a vector, the matrix in front of that later. So this is x, and we have n plus 1, and then we have a vector here and that is Tx, and Tx is in Rm, so it is m equals 1. So the matrix, in order to multiply to n by 1, that gives us m by 1, it have to be m by n, because n and n middle numbers must be the same. Then the outside m by n give us the dimension of the product. So if that's confusing, let's just say we have ax equal to tx, t of x, and t of x is in Rm, so this is m by 1, and x is n by 1, therefore a has to be m by n. Right. As mentioned before, the middle numbers must be the same, and we have outside numbers as the dimension of the product. So that's what we have. Now let's go to this example. Find t of u, the image of u under the transformation t. If this is a and this is u, the transformation t go from R2 to R3 given by transformation of x is equal to a times x. So it's easy enough. So we say t of u, transformation of vector u, is equal to a times vector u, and a is the matrix 1, negative 3, 3 and 5, negative 1 and 7. Times u, 2 and negative 1. Right. Once again, multiply row times column. So first with the first, I'm just going to write down 1 times 2 plus negative 3 times negative 1. So that first row, first column. Second row, second column, 3 times 2, 5, negative 1, and then negative 1 times 2 plus 7 times negative 1. Right. So we have 2 and 3, that's 5. 6 minus 5, negative 2, negative 7. Right. Sorry. Just multiply the matrices. 3 rows, 2 columns. 1, negative 3, 3 and 5, negative 1 and 7 times the column vector of two rows, 1 column of 2 and negative 1, 5, 1 and negative 9. So yeah, that's straightforward. Right. So the transformation of a vector defined by a matrix, we just take the matrix times the vector. Sorry. Now, find an x in R2 whose image under T is B, right? So we will say x is in R2, which is in the domain. R2 is in the domain, so we say T of x, which is equal to A times x. And this said the image under T is equal to B, so this has to be equal to B. Alright. So we will say the matrix A 1, negative 3, 3 and 5. Let's plot a little bit bigger. Negative 1 and 7. Times x. We're just going to say x equal to b 3 to negative 5. Right. So of course that matrix equation. So we put in the matrix this on the left hand side, this on the right hand side. 1, negative 3, 3 and 5. Negative 1 and 7. This is on the matrix. So the matrix on the left hand side, the columns of the matrix from the left hand side, and then the right hand side is the image. And now we do the reduced row echelon form. Three rows, 3 columns. 1, negative 3, 3, 3, 5, and 2, and negative 1, 7, and negative 5. Right. I am going to change the fraction, so that's what we have. So 1, 0, 3 half, 0 and 1, negative 1 half, 0, 0, 0. Right. Now, remember the x here. So x is in R2, right? So if we want to write x as a matrix, as a vector, so we should write 1, negative 3, 3 and 5, negative 1, 7. X we know it's going to be in R2, so we'll have 2 components. So we have 2 corresponding x2, x1, and x2. Both of them have the pivot entry. So with the first equation, x1 equal to 3 half, x2 equal to negative 1 half. Right. So in this case, the question is there more than one x whose image under T is equal to b. So we have a times something equal to b, and when we solve this equation, we only have x1 equal to 3 half and x2 equal to negative 1 half. There's no other solution, right? Yeah, because from the equation, that's all we have. There's no free variable here. So the answer is just simply no, because we solved the equation, the matrix equation, also one solution. So there's only one x, x1 equal to 3 half and x2 equal to negative 3 half. And that's pretty much it. Only one solution. Or we say x is equal to 3 half and negative 1 half. That is the unique solution. So we say x 3 half and negative 1 half is the pre-image of B. Right, so that will work that definition of the pre-image into problem. Now determine if C is in the range of the transformation. Right. So now we have C is that. So is C in the range? What is the range? the range is the set of all the images Tx. So the question determines if C is in the range of the transformation. Again, we said if we find a transformation Tx equal to a times x, and if C is in the range, meaning that is this one has the solution. If it has a solution, that means there is an x that gives us a c. So c in that case have to be in the range. If there's no solution, then we say c is not in the range because there's no x that gives you a c in the codomain, right? So we write that, and the question is there a solution? Right, a sub x, the matrix A is going to be this. The matrix X, we don't know what it is, but X is in R2, so it has two components, X1, X2, and equal to C 3, 2, 5. Right. Now, once again, I put in the matrix matrix and do the reduced row echelon form. Matrix matrix, so it's just a straight line. Reduce row echelon form. Right. So just copy and paste what I have there, because the first part still good. 1, negative 3, 3, 3, 5, 2, negative 1, 7, and 5. So I only need to change the last number. And this is what we have. Right, so there are two columns corresponding to x1 and x2. And we have the pivot here and the pivot there. Right, but what do we have in this problem? What we have here is the pivot on the last column of the matrix matrix. When that happens, we have no solution, because if we write it down 0x1 plus 0x2 equal to 1, right? If I write this out corresponding to this row, 0x1 plus 0x2 equal to 1, that's impossible to have 0 equal to 1. So in this case, when we have this, that is no solution. So is there a solution? The answer is no solution. So then the question is C in the range of the transformation? In that case, the answer will be no. C is not in the range of the transformation. Doesn't matter what x is, we will never have C when we transform x. Doesn't matter what x is, the image will never be C, because this is no solution. So we say C is not in the range. Once again, doesn't matter what x is, the image is not going to be C. So C is not in the range of the transformation. Now let's look at some example here. projection. Let A be this matrix describe the image of X of A. So the transformation of X is given by a matrix A times X. Now let's work the dimension. This is the matrix A. And if we check the dimension of matrix A is 3 rows, 3 columns. So what is the dimension of the matrix X? Remember, when we multiply matrices, the middle number must match. So the X here have to be a vector that has 3 rows. So let's say X, Y, and Z, 3 components. So just choose X, Y, and Z. Right? Now let's just, of course, when we multiply, the middle numbers match. The outside number will be the dimension of the product. So when we multiply, the dimension will be 3 by 1. Right? But that's not important. Now just multiply now. 1 times X plus 0 times Y plus 0 times Z, and then 0 times X plus 1 times Y plus 0 times Z, and then the last one 0x, 0y, 0z. So when we multiply, we will have x, y, and 0. So the reason that I use x, y, z instead of x1, y1 and x1, x2 and x3 is what we see here is we have the coordinate x, y, z, and when we do the transformation we only have x and y. So what we actually have is here's this situation. Now let's look at the 3-dimensional coordinates. If we have a point here, x, y, and z, the transformation is going to be on the xy plane because we have x, y, and 0. So this transformation transform a point on space onto the xy plane. So that's why we consider this is a projection of a point on space onto the xy plane. Next, we have a shear. Let A be the matrix 1, 3, 0, 1. The transformation from R2 to R2 defined by this should be a vector x. It's called the shear transformation. Find the image of a 2 by 2 square. So we're trying to find the image of this. Right. So this image will have the following point. Obviously 0, 0. This point is x equal to 0, y equal to 2, and this one x equal to 2, y equal to 0, and the point 2 and 2. Alright. Now we're going to find the image of this point. So it's easy. A point is just like a vector, so I just take say t of x is equal to ax, and a is 1, 3, 0, and 1, and x, see x1, x2. Yeah, and then we just put all those points in. in particular t of 0, 0. Let's put 0, 0 as a vector instead of a point. Right, 0, 0 I'm going to use as a vector. Right, so we're going to have the matrix times the vector, because anything times 0 vector is going to be 0. So the map will map 0, 0 into 0, 0. That's easy. Next, t of 0, 2. This point 1, 3, 0, 1 times 0 and 2. 1 times 0, 0, 3 times 2, 6. And then 0 times 1, that will be 6 and 2. So it will map the point 0 and 2 to the point x equal to 6, y equal to 2. Next we'll find t of 2 and 2. Just take the matrix times the vector. So 2 plus 6 is 8, and then and 2. So 8 and 2, x equal to 8, x1 equal to 8, x2 equal to 2, and then 2 and 0. Just take the matrix times the vector. So 2 and 0 and 0. So it maps 2, 0 to 2, 0. Now, notice that in the linear transformation, what we have here, it maps a square into a parallelogram. Of course, the coordinates should be the same, but if we write that, there's not enough space. So notice that the point will be in this order, one clockwise orientation. So in this we have clockwise orientation. So it go from a square into a parallelogram. I should have these two in the same scale, but regardless, that's what we have. If we want to, we can draw the write the coordinate 6, 2 here, 8, 2, and 2, 0. Right, so this is the image of that, and or we say this is the pre-image of that. Definition: linear transformation. A transformation or mapping of T is linear if T of a sum is transformation of a sum is the sum of the transformation. Transformation of scalar multiplication is the scalar multiplication to the transformation. Right. Next, here's important things. Every matrix transformation is a linear transformation. Linear transformation reserve operation of vector addition and scalar multiplication. So when we have a matrix like this, it is called a linear transformation. Every matrix is a linear transformation. And the properties of linear transformation is that it transforms 0 into 0, exactly what we have here, right? For 0, 0 to 0, 0. And the linear combination, transformation or linear combination is the combination of the transformation. Right. Here's more example. Contraction and dilation. Given a scalar r, define t as r2 to r2, t of x equal to r times x. So pretty much whatever the vector we have, we just multiply by a number, so we could get bigger or smaller. If we get things get bigger, that's called dilation when r is bigger than 1, and contraction when it is less than 1 but still positive. Let r equal to 3. Find the transformation of the unit square 0, 1, 0, 1. So the unit square meaning that that is the unit square. The coordinates 0, 0, 0 and 1, 1, 1 and 1, 0, and we find the transformation of that when r equal to 3. So we say t of x is equal to r times x, so just 3 times x. Or if we write t of x1, x2 is going to be 3 times x1, x2, which is equal to 3x1, 3x2. So that's simple enough, right? Now the transformation of 0 and 1, I mean 0 and 0 first. Transformation is just multiply the coordinates by 3. So 3 times 0, 3 times 0, we still have 0, 0. That easy. Now let's find the transformation of 0 and 1. So transformation, just multiply the coordinate by 3, multiply that by 3, just 0 and 3. Now we find the transformation of 1, 0, multiply that by 3, 1 times 0, 1 times 3, and 0 times 3. And finally, 1 and 0, 1 and 1. I didn't write this in the order, but that's okay. 3 and 3. Bottom line is the transformation. We have 0, 0, 0 and 3. There will be 3, 3, and 3, 0. So transformation would turn this little square, the unit square, into a bigger square. That's called the dilation by the factor of 3. It's simple enough, right? Next, rotation. Define the linear transformation as t of x is that vector times x, which gives us negative x2 and x1. Find the image under t of u and v. So t of u is equal to the vector, equal to the matrix times vector u. So 0 times 4, 0, plus negative 1 times 1, negative 1. and then 1 times 4 plus 0 times 1. And then T of V (0, -1, 1, 0) times V so what do we have? 0 times 2, so that's -3 and 2. Right, so that is the image of U, the image corresponding to U, image corresponding to V. Now the image corresponding to U plus V will be the matrix times U plus V is going to be 6 and 4. Which give us -4 and 6. Right. That is all. However, since this is the problem, let's just explore a little more. So we have T of U plus V is that. Now, let's just do this to test what is T of U plus T of V. T of U plus T of V. T of U is that, plus T of V is that. And what we see here is that transformation of a sum is equal to the sum of the transformation, which it's supposed to be. Let's just draw it out and see why is this, what transformation this. Let's say we have the point here. x1, x2, and after the transformation it will go to -x2. Sorry, let's make it a little less special. So x1 is that, x2 is that. Now the transformation will turn into -x2 and x1. So the transform this vector into this vector, and it will actually draw a vector. This is original vector, or original point x1, x2. The image is going to be this. -2 x2 x1. So of course that of course is rotation. Right. That should be 90 degrees rotation. Yeah. Right. More simple. Suppose that the transformations go from R5 to R2 and Tx equal to A times X for some matrix A. What is the dimension of the matrix A? Right? So suppose T go to R5 to R2. So we write out very simple like this. Tx is equal to A times X. Now, A we don't know the dimension. We do know X is R5. So when we write like this, we mean X is in R5. So X the dimension for x is a vector in R5, so 5 rows, 1 column. Now the transformation will be on R2, so the result is going to be 2 by 1. The range is R2, so the column, 2 rows, 1 column. So what is the dimension of A? Right? 1 multiplied 5 by 1 is going to be 2 by 1. So the middle numbers must match on, it has to be something by 5. And the outside will give us the dimension of the product. So this has to be 2 by 5. Right? The middle number match. And then 2 and 1 give the dimension of the matrix. The matrix in R2. Right. Now, let A be 1, 0, and 0, negative 1. Give a geometric description of transformation x to A sub x. So let's say if we have a transformation of x is equal to AX. Vector matrix A is 1, 0, 0, negative 1. X, let's say generic x1, x2. Multiply 1 times x1 plus 0 times x2. So 1 times x1. And then 0 times x1 minus 1 times x2. So what do we have here? So we have upon x1, x2, the transformation will turn into x1 and negative x2. So this is the x1 coordinate, x2 coordinate. The coordinate x1, the first component stay the same, but the second component is going to be opposite. So I write that as a point. Remember, a point is a vector, and the vector can be thing as a point. So this is originally x, and then so this is x. This is t of x. So just mirror image the reflection on the x-axis. So this is a reflection. Reflection on the x1 axis. x1 will stay and x2 turn to opposite. Next, show that t transformation of x1, x2, the point is given by this is not a linear transformation. So the linear transformation will have two properties. It transforms a sum into the sum of transformation, and it transforms a scalar multiplication into that. What we have is this transformation. So, and yeah, up to this point we write the transformation is in the vector form and the matrix form. Of course, we can write like that too. Of course, that we should turn into a matrix if we want to. Remember, a vector is not just a column vector. I mean, a vector is just something that has more than one component. So we can write like that, or we can write as that. And it has 3 components here. 2x1 plus 3x2 negative 3x1 minus 4 and then 5x2. Now, the reason that why this is not a linear transformation is what? Because the negative 4 here, you can it doesn't attach to either x1 or x2. That's why it makes this not a linear transformation. Right? Think about it this way. And the reason that this is not a linear transformation, right? That's why we did not write this as a times x, right? Because if this is a linear transformation, we should be able to write this as the matrix multiplied to a vector. This is not a linear transformation, so that's why we cannot write this as the matrix times a vector. We can write that as something else, but this is not going to be a linear transformation, so we cannot put in that matrix form. Right? Now, I mean, I can write like that, but I cannot say it equal to a times x, and that is impossible to do that because of the negative 4. Right? What we do instead to show that this is not a linear transformation, of course we can use any of this, but the easiest one is a linear transformation. You transform 0 to 0. So let me write this linear transformation. If it is a linear transformation, then a transform of 0 vector is equal to a 0 vector. So now we just do the transformation of a 0 vector will be 0 and 0. Right? 2 times 0 plus 3 times 0 minus 3 times 0 minus 4 and 5 times 0. So do all of that, we have 0, negative 4 and 0. So the transform of 0 is not, it gives us a 0 vector. So this is not linear transformation, because a linear transformation we have these properties which we do not have. So T is not a linear transformation. Right. Linear transformation has a lot of different properties by definition, but we use the easiest properties. That says transformation of a 0 vector is a 0 vector, which we do not have. Because there's not a linear transformation, we cannot put that in the matrix form of a matrix times a vector. Right, so that's all we have in this section. We just define a linear transformation, I mean a transformation, and then a linear transformation which can be written in the matrix form. And then we just have some basic one like projection, shear, and later on we have also reflection. But that's all we have for this section. As always, thank you for watching, and see you in another video in linear algebra.